Hey guys, this is Mrs. Harbin, and this is Pre-Cal, and we are on Chapter 2, looking at 2.3 quadratic functions. We've been reviewing linear functions, graphing those, and writing equations for those. Now let's take a look when our functions don't make a straight line, when they are quadratic. Our life application is that you, the student, will be aware of angles in creation. Just as each geometric angle has a precise measurement when properly aligned with a measuring tool, so to the angle that the student's life takes will have a precise direction if he is properly aligned with God's Word. We know precision is important not only in math, but to God we see precision all throughout His Word. He's very careful to tell us precisely what we need to do and the choices that we need to make, and it is up to us to use His Word as our measuring tool to make those decisions. Our lesson objective for today is that you, the student, will graph quadratic functions and identify the maximum and minimum point and any zeros of quadratic functions. So let's think about first what a quadratic function is. Let's talk about the meaning of the word quadratic. Hey, quad, hopefully you know. Quad means four. You've got your quadricep muscles in your legs. There's four there. You know, a quadrilateral is a four-sided shape. And when you think about things that there are four sides of, hopefully the shape that you think of is a square. And you know that, for example, if the side of our square is 4 units long, then to express the area of that square, we would say it is 4 squared, or 16. Well, if we don't know the side of that square, let's say the side of our square is x, we would say that the area of the square is x squared. So quadratic functions are always going to have a squared term. And hopefully relating that to that four-sided shape of a square, that quad, will help you remember that. But a quadratic function is a function in the form f of x. Remember, f of x is just y. F of x equals ax squared plus bx plus c, where a and b and c are real numbers, a and b are coefficients, and c is a constant term, and a cannot be equal to 0. So let's take a look. Here's a quadratic function. We've got our a, which is 3, our b, which is 1. You don't have to write it. We know it's assumed here. And our c, our constant term, is -7. And we've got this square exponent here, so we know it's a quadratic function. And our example says to find the set of ordered pairs described by the function f of x equals 3x squared plus 1x minus 7 in the domain -3, -2, 0, and 2. Essentially, remember, these are our x values. And what we're going to do is plug each of those into our f of x, our function here. Think of it like a little machine. Plug them into the function and figure out what the output is. So when we plug in -3, we get 17. When we plug in -2, we get 3. When we plug in 0, we get -7. And when we plug in 2, we get 7. So our ordered pairs there are -3, 17, -2, 3, 0, -7, and 2, 7. The shape of a graphed quadratic function is called a parabola, and that is going to be this kind of U shape. It can open up or it can open down. This should be a review for you from last year. The corresponding three-dimensional shape is called a paraboloid. So if you think about like a bell, for example. A bell is kind of a parabola shape, but it's rounded. Put the side there, and you've got the handle, you know, if you're talking about a hand bell. Some other things that are paraboloids, we have satellite dishes, which has that, again, that parabola shape here, but it's three-dimensional. Bowls are paraboloids. So there are a lot of things that are paraboloids, that are three-dimensional parabolas. Let's take a look at these graphs and compare their equations. On the left, we have y equals x squared. This is what we're going to call our parent graph, our x squared graph. It's our basic, just very simple quadratic formula graph where our coefficient in front of our squared term is 1, and we don't have an x term or a constant term. It's just y equals x squared. Well, how does the graph on the right compare to the graph on the left? What are some things that you notice? Okay, hopefully on this graph you notice that the vertex, that's not really a vertex, apex, whatever you want to call this. This is at 0, 0. We'll go over the official term later. And that it's opening upward. On this graph, you can see that the peak here is at 3, 4, and it's opening downward. So how does that look when we look at their equations? What are some things that are different? Well, we have a constant term here, 4, and our x term has, or our squared term has an x minus 3. Well, I know that 3 and 4 are the 2 points that I listed right here for my vertex, 3, 4. I also notice that in front of my squared term, I have a negative 2. I'm wondering then if that negative has something to do with the direction that the parabola opens. So this form that we just saw on the right, y equals a times x minus h squared plus k, is the standard translated form of the parabola. The standard translated form of the parabola. It's also called the work form. So when you're asked to put it in work form, that's what we're referring to. A variation of this is y minus k equals a times x minus h squared. By subtracting that k from this side and subtracting a k here to keep it balanced, that gives us our secondary or alternate form. And what this form tells us is the vertex of the parabola. I called it apex, I think, when I was talking earlier. But this h and this k, these two numbers, are the vertex of the parabola. If a is greater than 0, the parabola opens upward and it has a minimum point. So we saw in that first parabola, the coefficient in front of our square term was 1, which is greater than 0, so it opened up. And our second parabola that we were looking at had that negative 2. Negative 2 is not greater than 0, so it opens downward. When it opens upward, we have a minimum point. We have a valley down here, a vertex on the bottom. And when it opens downward, then we've got a peak up here, kind of the top of a mountain or maximum point. Let's take a look at this example and see if we can graph y equals 3x squared plus 12x plus 8. Give the domain and range. So first thing we want to do is put it in standard form or work form using completing the square. So in case you forgot how to complete the square, let's review those steps. First, we need to make our x squared coefficient 1. And we're going to do that by factoring a 3 out of our first two terms. Sorry for the dog barking in the background. I can't get him to be quiet right now. So when I factor 3 out of those first two terms, I'm left with x squared plus 4x. So that's the first thing that I want to do. The next thing that I'm going to do is to complete the square. So what I need to do is take my number that I factored out here. We're going to take this term. Sorry, I had to pause and take care of the dog, and I don't remember what I was saying or where I left off, so let's try this again. We're going to complete the square. We're going to take our b term here, that 4 term, and we cut it in half and then we square it. In this case, taking the 4, cutting it in half, gives us 2, and squaring it just gives us a 4. And we add that inside the parentheses. But in order to keep things balanced, because we added a 4, what we actually added was 3 times 4. So in order to keep that equation balanced, so equal to y, we also needed to subtract 3 times 4. So we're going to do that outside the parentheses. So by adding that 4, that 3 times 4, to keep it balanced, we have to have a minus 12 or a minus 3 times 4 on the outside. Then we're going to simplify that equation by factoring. And that leaves us with, since a equals 3, we know the graph opens upward and it has a minimum value. And this is going to give us our h and our k, our coordinates. Our vertex is going to be negative 2 and negative 4. Remember, standard form is x minus. So because this is a positive, we know it's x minus negative 2 to get that vertex there. Our domain will be all real numbers. And your graph should look something like this. Vertex at negative 2, negative 4, opening upward, and all real numbers. Our range is that y must be greater than or equal to -4. Because it opens upward, this is our minimum point. We cannot go any lower than that in our range. The axis or line of symmetry cuts the parabola in half, and it passes through the vertex. Its equation is x equals h. So if we go back and we look at our picture here, our line of symmetry would go right through this point, x equals -2. And that would be our line of symmetry, which is what that h point was. When we talk about the zero of a polynomial, what we want to know is where it crosses the x-axis, essentially. But the formal definition is this. The number r is a zero of p of x if and only p of r equals 0. The root of an equation is the number that is a solution of an equation. Let's find the zeros of y equals -x² minus 6x. So first things first, we're going to set this equal to 0. Then we're going to factor, starting by factoring out the -x. We'll take both of our factors and set them equal to 0. We know that one of these two factors has to be equal to 0 in order for the whole equation to be equal to 0. One of those would have to be equal to 0 as well. So we get -x equals 0 or x plus 6 equals 0, which leads us to x equals 0 or x equals -6. Sometimes the quadratic formula is needed to find the zeros. And I'm sorry I don't know the quadratic formula song, but hopefully you can remember that and remember how to use the quadratic formula. Find the zeros of f of x if f of x equals 5x² minus x plus 2. We're going to set that equal to 0. Unfortunately, that does not factor neatly, so we do need to use the quadratic formula. And there it is on the right-hand side as a reminder.